Imagine a star, millions of times bigger than our sun, suddenly exploding in a brilliant display of light and energy. This is the story of supernovae. These are not just any ordinary explosions. They are the spectacular, violent deaths of massive stars, sending shockwaves across the cosmos and birthing elements that make up the universe as we know it. In the grand scheme of astrophysics, supernovae play a pivotal role. They are key to understanding the life cycle of stars and the cosmic processes that shape galaxies. But what exactly are these celestial fireworks and how do they come about? Picture a star much like our sun, but significantly larger. Over the course of millions or even billions of years, these stars live a relatively peaceful life, burning hydrogen in their cores to produce helium and releasing a steady stream of light and heat. This is the process known as nuclear fusion, and it's what keeps a star shining bright. But stars aren't immortal. Once they exhaust their hydrogen fuel, things start to change dramatically. The star begins burning heavier elements, creating an onion-like structure of different layers, each burning a different element. Eventually, the star starts producing iron in its core, a point of no return. Iron cannot be burnt for energy, and so the core collapses under its own gravity, rebounding in a cataclysmic explosion. This, in essence, is a supernova. These stellar explosions are not just fascinating events to observe, they are also astrophysical laboratories offering us insights into the forces at play in the universe. The energy involved, the particles accelerated, the light emitted, all provide clues to the fundamental workings of the cosmos. Now that we know what supernovae are, let's delve deeper into the life and death of these celestial giants. From their birth in dense clouds of gas and dust, through their long lives burning hydrogen, to their dramatic ends as supernovae, each stage of a star's life is a piece of the larger cosmic puzzle. Not all stars are destined to become supernovae. It takes special conditions and a lot of mass. In the vast cosmic arena, the birth of a star begins in a similar fashion, regardless of its eventual size. Amidst the interstellar medium, we find giant molecular clouds, vast regions brimming with gas and dust. When these clouds are perturbed, perhaps by the shock wave from a nearby supernova, regions within them begin to collapse under their own gravity. As these collapsing regions shrink, they heat up and form protostars. The gravitational pull of these nascent stars attracts more and more matter, causing them to grow. But here's the catch. Not every protostar will grow to become a massive star. Only those with enough mass to ignite the nuclear fusion of hydrogen into helium in their cores will graduate to main sequence stars. Now, what does it take for a star to become massive, to become one of the titans of the cosmos? It's all about the initial mass of the protostar and the amount of available material in its vicinity. If a protostar starts with a hefty amount of mass and resides in a dense part of the molecular cloud, it can accumulate enough matter to become a massive star. These massive stars, often weighing in at 8 or more times the mass of our sun, are the ones with the potential to end their lives as supernova. They are the ones with cores hot and dense enough to fuse heavier elements, from helium all the way up to iron. Gravity plays a crucial role in this process. It's the force that initiates the collapse of the molecular cloud. It's the force that pulls in the surrounding material to form the star, and it's the force that keeps the star stable once nuclear fusion begins. With the right conditions, a massive star begins its journey, one that could end in a spectacular supernova. Their lives are relatively short, but they burn brightly, contributing significantly to the enrichment of the universe with heavier elements. And when they die, they do so in a grand spectacle, leaving behind a legacy that continues to shape the cosmos. A star's life is a constant battle against gravity, with nuclear fusion as its weapon. Picture this. A massive star, born from a dense cloud of dust and gas, begins its life in a state of equilibrium. The inward pull of gravity is perfectly balanced by the outward pressure from the energy produced by nuclear fusion in the star's core. In the heart of the star, a high-temperature, high-pressure environment facilitates the fusion of hydrogen atoms into helium. This dance of atoms, this transmutation of elements, is what fuels the star and generates the heat and light we see from billions of kilometers away. But what happens when a star exhausts its supply of hydrogen? The answer lies in the life cycle of massive stars. The star doesn't simply flicker out. Instead, it transitions into the next stage of stellar evolution, triggering helium fusion, which produces carbon. As the star ages, it continues to fuse heavier and heavier elements in its core, from carbon all the way up to iron. This process of fusion in the core of the star is akin to a cosmic factory, producing the elements that make up the universe. But the factory has its limits. Once the core of the star is filled with iron, the star can no longer generate enough energy to counteract the force of gravity. Now, the star is at a crossroads. If it's massive enough, it won't go gently into that good night. Instead, it will go out with a bang, in a supernova explosion. However, if the star is not massive enough, it will shed its outer layers, leaving behind a white dwarf. So the life of a star is not just a tale of light and heat. It's a story of cosmic transformation, of the life and death struggle against gravity, and of the birth of elements that make up our universe. As the star burns through its nuclear fuel, it sets the stage for a potential supernova. And that, dear listeners, is where our story takes a truly explosive turn. But that is a tale for the next scene. Not all supernovae are created equal. Indeed, these spectacular stellar explosions come in a variety of types, each with their unique characteristics and conditions for formation. The two main categories are Type 1 and Type 2 supernovae. Let's delve into what sets them apart. Type 1 supernovae are the sneaky ones. They occur in binary star systems, that's a pair of stars orbiting around their common center of mass. One of the stars in this duo is a white dwarf, a compact stellar remnant. The other could be anything from a giant star to even another white dwarf. The white dwarf star, being quite the gravitational bully, siphons off matter from its companion. Over time, as it continues to accumulate matter, the white dwarf reaches a critical mass, leading to a catastrophic explosion. This is a Type 1 supernova. Now, let's turn our gaze to Type 2 supernovae. These are the dramatic ones. Type 2 supernova involve a solitary massive star that has exhausted its nuclear fuel. The star's core collapses under its own gravity, resulting in a violent explosion. Interestingly, these two types of supernovae can be distinguished by their light spectra. Type 1 supernovae lack hydrogen lines in their spectra, while Type 2 supernovae show prominent hydrogen lines. So what conditions lead to each type of supernova? For Type 1, it's all about the binary system and the relentless gravitational pull of the white dwarf. For Type 2, it's the solitary star's internal battle against gravity once its fuel reserves are depleted. Whether Type 1 or 2, each supernova is a unique and powerful event. They are the universe's most grandiose fireworks, painting the cosmos with light and spreading elements necessary for life as we know it. Through understanding the different types of supernovae, we gain deeper insights into the life cycles of stars, the workings of the universe, and even our own cosmic origins. In the final moments of a massive star's life, it releases more energy than our sun will output in its entire lifetime. The energy of a supernova is so vast, it's hard to wrap our heads around it. Let's try to break it down. A supernova is the explosive death of a star, and it's one of the most powerful events in the universe. When a star goes supernova, it releases a colossal amount of energy. How colossal, you ask? Well, let's put it this way. A single supernova can outshine an entire galaxy, which contains billions of stars. This energy isn't just light and heat. A supernova's shock waves can trigger the birth of new stars, while its expelled material enriches the interstellar medium with heavier elements. These elements are the building blocks of new stars, planets, and even life itself. So in a way, supernovae are cosmic forges, shaping the universe as we know it. Now, how does the energy output of a supernova compare to a star's lifetime output? As a reference, consider our sun. It's been shining for about 5 billion years and will continue to do so for about 5 billion more. Yet, the energy a supernova releases in just a few months is more than the sun will emit in its entire 10 billion year lifetime. Staggering, isn't it? But it's not just about the energy. The process of a supernova explosion also creates a variety of exotic particles and phenomena, such as neutrinos and gravitational waves, which are subjects of intense study in contemporary astrophysics. In the grand cosmic drama, a supernova is the ultimate finale, a spectacle of energy and matter that shapes galaxies and births new stars. It's a testament to the incredible forces at play in our universe, forces that can create and destroy on a scale that is truly awe-inspiring. The energy of a supernova is truly mind-boggling. It's a reminder of how dynamic and ever-changing the cosmos is, and how much there is still to discover. How do we know when a supernova occurs in the cosmos? A question that has intrigued many curious minds. The answer lies in the observational signatures of these celestial events. Astronomers detect supernovae using a variety of methods. One common method is through sky surveys. These are systematic observations of the sky conducted with telescopes that capture images of the cosmos. When a new point of light appears in these images, it could be an indication of a supernova. Another method is through the detection of neutrinos. These elusive particles are produced in vast quantities during a supernova explosion. They travel at near light speed and can reach Earth before the light from the supernova does. Large underground detectors are used to capture these neutrinos and alert astronomers of a potential supernova. The light produced during a supernova explosion provides valuable information about the event. This light is not limited to what we can see with our eyes. Supernovae emit light across the entire electromagnetic spectrum, from radio waves to gamma rays. Observations in different wavelengths give us a more complete picture of the event. For instance, optical observations can reveal the location of the supernova and its host galaxy. Infrared observations can provide insights into the dust and gas surrounding the supernova. X-ray and gamma-ray observations can unveil the high-energy processes occurring during and after the explosion. A supernova explosion is also a significant source of gravitational waves. These ripples in space-time are produced when massive objects accelerate or decelerate. The detection of gravitational waves from a supernova could provide us with a new way to study these events. Yes, the universe is vast and filled with mysteries, but the tools and techniques developed by astronomers allow us to unveil these mysteries one by one. Supernovae, these massive explosive events, are no exception. Thanks to modern technology, we can observe these celestial fireworks from the comfort of our planet. A thought that should fill us with awe and admiration for the wonders of the universe and the ingenuity of human innovation. A supernova doesn't just end with the star, it has far-reaching effects on the surrounding space. Imagine a cosmic bomb detonating with the energy of 100 million suns. This cataclysm sends shockwaves rippling through space, perturbing nearby celestial bodies and stirring up the interstellar medium. As these shockwaves travel, they sweep up an enormous shell of gas and dust. This cosmic debris can trigger the formation of new stars and planetary systems. Over time, the supernova remnant expands and cools, creating a nebula, a glowing testament to the star's explosive death. But that's not all. These stellar explosions also seed the cosmos with heavy elements that are essential for life as we know it. Everything from the iron in our blood to the silicon in our computers can trace its origin back to the heart of a dying star. So you see, a supernova is not just a cosmic spectacle, it's a cosmic creator. The aftermath of a supernova can be just as interesting as the event itself. Even in death, a star leaves behind a legacy. Supernovae, the explosive deaths of massive stars, are not just dramatic cosmic events. They are also the cosmic crucibles where some of the most exotic celestial bodies come into existence. When a star exhausts its nuclear fuel and explodes as a supernova, it doesn't simply vanish. Instead, it leaves behind a dense core, a stellar remnant, which can take the form of a neutron star or a black hole. Neutron stars are the smallest and densest stars known to exist. They are essentially giant atomic nuclei packed with neutrons. These remnants are about 20 kilometers across but have masses greater than that of the Sun. Imagine the mass of a star, similar to our Sun, squeezed into a sphere with a diameter smaller than a city. That's the kind of density we're talking about. Black holes, on the other hand, are regions of space where gravity is so strong that nothing, not even light, can escape from them. They're called black holes because they absorb all the light that hits them, reflecting nothing. These fascinating entities are the end result of the most massive stars' lives. But why are these remnants so important? Well, they provide us with unique laboratories to test the laws of physics under extreme conditions. The extreme densities and gravitational forces present in these objects allow us to probe the nature of matter and the universe in ways that are impossible on Earth. Moreover, these remnants play a crucial role in the cosmic cycle of birth and death. The material ejected by supernovae, enriched with heavy elements, scatters into the interstellar medium. This material can later condense to form new stars, planets, and even life. So in a way, we owe our existence to these stellar remnants and the supernovae that created them. From the ashes of a supernova, new celestial bodies are born. The study of supernovae and their remnants is not just about understanding the death of stars, but also about unraveling the secrets of life, the universe, and everything in between. Supernovae, the explosive deaths of massive stars, are some of the most powerful events in the universe. We've journeyed through the life cycle of these celestial giants, from their formation to their dramatic end. we've discovered that they play a significant role in shaping the universe, from influencing the evolution of galaxies to forging new elements. Supernovae are not just an end, but also a beginning, leaving behind fascinating remnants like neutron stars and black holes. Their immense energy, brighter than entire galaxies, provides a beacon for astronomers to study, offering clues about the mysteries of our cosmos. But our journey doesn't end here. There's a vast universe of knowledge still to be explored. The study of supernovae is a rapidly advancing field, with new discoveries and theories emerging regularly. So let's keep our curiosity ignited, continue to delve deeper, and keep our eyes on the stars. The more we learn about supernovae, the more we understand about the universe and our place in it.